everybody for being back. So I think this was now communicated widely, but just let me stress again. So the slides, I prepared the slides in advance. So if you want to go back also to what I was saying, 2 slides before, you can just download the slides from the website. And, right. Okay, now, so it just told me that now my video is visible for everybody. And so the plan for today is to introduce the Gaussian analysis that we need to study this problem of constructing the generator for Burghers equation. Then to go ahead with the construction, so to construct the operator, and then to prove the existence of solutions to the martingale problem. And then the last lecture on Thursday, we will prove the uniqueness of solutions to the martingale problem, and I will present this new approach with which we can do critical equations. So if you pay careful attention today, you will see that there is still heavy use of subcriticality at some point. So what did we do yesterday? We considered this Burghers equation. And the problem with this equation was the lack of regularity, because the solution is like a white noise in space. So we don't know what its square is. And our aim is to construct a martingale problem for this equation. And so the problem was even defining the generator would not make sense, because you cannot evaluate the generator on the simplest test functions. You cannot evaluate it on the state space for all points. So we had the idea that maybe we could do it for almost all points on the state space, which of course only makes sense if we talk about a measure. So we need a measure for the analysis. And yesterday I tried to convince you that this measure should be the law of the white noise, because this is the invariant measure for this equation. So it should be invariant. And it was a bit formal. We showed that it's indeed invariant for the linear dynamics. For the nonlinear one, I gave you a formal argument why it should be true. And now we want to do analysis under this measure, and this is where we stopped yesterday. So we want function spaces with respect to our Gaussian measure. And so of course there are LP spaces, but we want to measure regularity. And for that purpose, we want to have some equivalent of these Sobolev spaces that you would have on a finite dimensional torus. So the question is, so these are defined in terms of the Fourier coefficients, the decay of the Fourier coefficients. So the question is if we have something like a Fourier transform on this L2 of mu space. And the answer is yes, and this is given by the chaos decomposition. And this is what we will show in the end. Now I will take 3 slides or so to derive this. So we will show that, and of course, probably many of you know this, but anyways, I want to present this slowly so not to lose anybody. So any L2 random variable with respect to our Gaussian measure has an equivalent representation in terms of an infinite sequence of functions over finite dimensional spaces. So this thing here takes as an input some omega, and the omega comes from the state space of this measure, so from the state space of the white noise. So it takes as an input a distribution of regularity -1/2, minus a bit. So it has an infinite dimensional input. And we will encode it by an infinite sequence of functions with finite dimensional inputs of growing and growing input dimension. And this is the chaos decomposition of this random variable. So how do we go about it? The idea is that for such functions here, we can define something what's called multiple Wiener-Ito integrals. And by summing up all these multiple Wiener-Ito integrals, we will get back this x here. So how do we construct these integrals? The easiest way to go about it is to note that if we have a white noise, then you can represent this white noise in terms of a Brownian motion as follows. So you just integrate the function phi, which you plug into the white noise, against the Brownian motion. So this is basically saying the white noise is the derivative of the Brownian motion. And now if you have a function of n parameters, then you would like to define something like, and then phi, and then db1, db, and this should be maybe t1, t2, until db tn. This should then be the nth, so the n-fold Wiener-Ito integral of this function phi. The problem is that then as soon as you take the first integral, it will be random and not adapted with respect to this Brownian motion, so you have a problem. But what you could do is, well, not integrate over the whole space. So here we take the first integral, and now we don't go all the way until 1, but instead we only go until x2. So we look at x1 less than x2. And after that, we have to integrate with respect to the Brownian motion be x2. But since this here is x2 measurable, that's fine. And in this way, recursively, you see that this whole integral is well defined because we ordered the times in that way. Of course, this ordering is quite arbitrary, right? So why should we, I mean, this here is somehow a function of n spatial parameters. Why would we now take x1 less than x2 up to less than xn? I mean, you could also take x5 is less than x17 is less than x3 is less than x1 and so on, right? So this would be equally valid. So we should somehow robustify our definition, not make it depend on this specific ordering of the points. And we can do this if the phi is symmetric. So symmetric means the symmetric function is a function which does not change if we permute the arguments. So here the sigma is any permutation of 1 to n, and we permute the indices and we get the same value. So any phi which satisfies this for all permutations is called symmetric. And if you have a function, then you can always define its symmetrization as follows. Well, you just take all possible permutations and apply them. And this is a sum over n factorial term. So to normalize, you divide by n factorial again. Now this here is a symmetric function, which somehow is something like a symmetric representative of your original phi. And now this definition makes sense. Now when we integrate this one here, so this is the same integral that we had before. For the symmetric function, then this is the same if we would now choose a different ordering here. So x3 less than x2 less than x4 less than x1 would give the same value because this phi tilde is symmetric and we always use the same Brownian motion here. So now actually the ordering doesn't play any role anymore, and this is, well, just one possible ordering. But of course, by doing that, we're not integrating over, I mean, we wanted to integrate something like this n-fold. So now we're not doing that. So we cut the space. But, well, if we sum back over all the potential different orderings, then we get the whole 0, 1 to the n. And for each ordering, we get the same value, like I just said. It doesn't depend on it anymore because the phi tilde is symmetric. So we just can also multiply with n factorial rather than writing down lots of different integrals which all give the same value. Right? So each ordering would give the same integral. So that's why we have n factorial times this integral. And this we define as Wn of phi. So this is the nth Ina-Ito integral of phi. And this is not defined in terms of phi itself, but in terms of the symmetrization of phi. So we can plug anything in L2 into it, but we only see the symmetrized version of the function we plug in. And then we have the following Ito isometry, which follows really from the usual Ito isometry, which you know from stochastic analysis. It's a 2-line computation. If you've never seen that, it's actually good to do this computation to check it for yourself. So this says if you take a function of n arguments, one of m arguments, and you multiply two such integrals together, then the expected value of the product is the Kronecker delta. So m has to be equal to n, otherwise it's 0. And if m and n are equal, so if they're both living in the same space, then you pick up n factorial here, and then here the L2 inner product of the symmetrizations. And now, next I want to convince you that this space is a closed space. So the image of this map here that we defined is closed in L2 of mu. And we can see this by introducing the so-called space of symmetric functions. So these are the equivalence classes of functions of n arguments with respect to the equivalence relation, where phi and psi are equivalent if one is a variable reordering of the other one. So I reorder the variables in psi and then I get back phi. So this is an equivalence relation that's easy to see. And we can define a norm on that space, which just assigns to each function the L2 norm of its symmetric representative. So each equivalence class on this space has one representative which is symmetric, and we just take the L2 norm of the symmetric representative. And then it becomes a Hilbert space, so in particular complete. And so therefore this map here is an isometry. So now we're interested in the case where n and m are the same here. So we see that up to this factor of n factorial here, it's an isometry from the complete space L2S into L2 of mu. And so therefore the image has to be closed, right? So the image of an isometry of a complete space has to be closed. So now we have seen that this space is closed. And well, from this relation, it also follows that Hn is orthogonal to Hm whenever m is not equal to n. So therefore we have that this direct sum here is contained in L2 of mu. So what we want to show next is that the opposite inclusion is also true, so that any element of L2 mu actually has such a representative, can be written as such a chaos series, we would call it. Right, so I forgot to say this. This space we call the nth chaos, this Hn here. I actually don't know where the name is coming from. So let's just take it as a name. Right, and now we want to show that any element in here actually has such a so-called chaos decomposition. Well, to see this, we can go to Hermite polynomials and study the link between Hermite polynomials and these chaos, so the Wiener chaos. The Hermite polynomials are defined as follows. So H0 is easy, that's just one. And Hn is defined recursively from Hn minus 1 by just multiplying it with x and then subtracting the derivative. And this is explicitly given by this formula here. So you just take a Gaussian density, basically, you differentiate n times. After that, you divide by the Gaussian density and you multiply by minus 1 to the n. You can check that this formula here satisfies this recursion. Okay, here are the first Hermite polynomials which you can compute. Just to point out, Hermite polynomials in different references are using different normalizations, and I always define them in such a way that the leading coefficient is 1. Based on this representation, it's easy to see that the Hermite polynomials are orthogonal polynomials, not orthonormal, but orthogonal polynomials for the standard Gaussian measure. So if we take the product of two Hermite polynomials of a standard normal variable, then we get n factorial for the expectation if n is equal to m and otherwise 0, which should remind you of the property that we saw for the chaos, right, for the nth and mth chaos. And, well, it should remind you because there is a link between Hermite polynomials and the chaos. So if phi is not equal to 0, phi being equal to 0 is not interesting because then the left-hand side is 0. But if phi is not equal to 0, and let's take a very specific function that we plug into this Wiener Ito integral here. So what is this function? This is just phi x1 times phi x2 phi xn. So that's, I denote like this tensorization. If we plug this function into here, which is of course a symmetric function, then you can write this as the Hermite polynomial of the white noise from which we constructed the Ito integrals, the multiple Ito integrals, divided by the L2 norm. So you normalize this one, so it becomes a standard normal variable, but because these Hermite polynomials, they seem to be linked with standard normal variables, right? Yeah, you can define Hermite polynomials for more general variances, but let's not worry about that. And well, since we divided it here, we somehow normalize it, so we have to make up for it. So we multiply it back with it here. And this is a polynomial with leading coefficient x to the n. And so here we will see this thing to the minus n. So we multiply with this to the plus n. And so therefore, the leading coefficient of this polynomial here will just be this variable to the n. Right, so from this, you can then, by some limiting argument, see that any polynomial in variables like eta tested against phi 1 up to eta tested against phi m is contained in this direct sum here. So we want to show that this direct sum here is the whole space L2 of mu. Now we show that all the polynomials of this form are contained in there. So to show that the whole space is equal to this thing here, we have to show that the orthogonal complement of this thing is 0. Right? But the orthogonal complement of this thing contains the orthogonal complement of all these polynomials. And now it is important what sigma algebra we take on this L2 space. And here we take the sigma algebra generated by our white noise. I mean, if we take a bigger sigma algebra, we could not hope to represent everything as a function of the white noise. So since we have the sigma algebra, anything that is in the orthogonal complement of this thing here has to be 0, and so therefore everything in the orthogonal complement of this direct sum has to be 0, and so therefore we have shown that this identity holds. And here I just plugged back in the definition of this Hn. So it's the Wiener Ito integrals of n-dimensional L2 functions, which are symmetric. Right, and so in other words, if x is in L2, then there exists a unique sequence of functions phi n, where the nth function is in LSTn, such that x can be written as this sum here, and the expectation of x squared is the sum of n factorial, and then here we take the L2 norm, well, the L2s norm of phi n, which is the L2 norm of the symmetric representative of phi squared. And we will now rather want to work on this space, because this is easier to deal with. So we define this as the Fock space, so which is this direct sum here. And well, this space we equip, well, exactly with this norm, right? So the norm of phi squared. So the norm, the L2 norm on this space, which we denote by gamma L2, I will never give a subscript. So it will always just be written like that. And this is by definition this here, sum over n factorial. This came from the n factorial in the Ito isometry, this n factorial here. And then the squared L2 norm of the symmetric representative of our kernel. Yeah, I don't think this will play a role for us, but one useful observation is if you work with these spaces, sometimes you will see a representation of on your Fock space of your kernels, which is not symmetric to start with. And then, well, here you always see the L2 norm of the symmetrization. And the point is that by the triangle inequality, you can pull this thing outside here. And then the L2 norm of this reordering of the variables doesn't change, right? So this has the same L2 norm as psi. So you have 1 over n factorial, sum over n factorial terms, which are all the same. So we can bound this by the L2 norm of psi. So this is always an upper bound for the symmetrization. So if we don't want to use the symmetrization, we could bound this thing and then control the quantity that we actually need. But yeah, so like I said, this is not so important, but this now is becoming important. This will be very important later. We have two notions of regularity on this space, on this Fock space. One is we can look at the regularity of the single kernels. So we could, for example, assume that the nth kernel is in H alpha. So maybe alpha is 10 or so. That means we can differentiate this kernel 10 times and we still have an element of L2. But we can also measure the decay in n. Yeah, so for example, we could assume that we don't take the usual norm where this term would not be there, but instead we multiply here with 1 plus n to the 2 beta, and then we ask that this is finite. And then the beta could be positive or negative, and depending on that, we now enlarge our space or make it smaller. And basically the whole story of doing this analysis is how we can deal with the interplay of these two different notions of regularity. So let's define Sobolev spaces. So H alpha beta are essentially those functions on the Fock space for which the H alpha beta norm is finite. What is the H alpha beta norm? Well, here we have the square, then we sum over all n, 1 plus n to the 2 beta. The 2 here is because of the square here, and the square here. And then we put a 2 alpha here, which is not so natural. It would be more natural to put an alpha here. I mean, the square is already appearing here. But it makes sense later. Essentially, it's because the generator, well, okay. It will make sense later that we have 2 alpha here. It makes some considerations a bit easier. Yeah, and here I'm just spelling out what this means. You sum over the Fourier modes and you multiply with this weight here where you have this 2 alpha, and the square here is coming again from the square. All right, and one important remark, if alpha is negative or beta is negative, then this is a smaller norm than the L2 norm. And in particular, L2 with respect to this norm would not be complete anymore. So we have to take the completion of L2 with respect to this norm to obtain a complete space. And then this space with negative regularities here would be the dual space of the corresponding space with positive regularities. This is how you could imagine it. And yeah, so one remark here. So this is also crucial. If alpha and beta are both positive, then we take a subspace of L2. And in particular, anything of this gamma L2 can be mapped back to random variables in L2 of mu. So if alpha and beta are positive, then these are random variables. If alpha is negative or beta is negative, then now we lost track with reality, so to say. No, we came from something which made sense, which was the invariant measure of our process, and we found an isometry to this Fock space, where we found a representation in terms of these kernels. And now we take an element which somehow looks like it would be in the Fock space, but it doesn't really have the regularity that you would require. And well, this element now can be seen as some dual element on the Fock space of some nicer objects on the Fock space, but you cannot push it through our isometry based on the chaos decomposition. And in particular, yeah, you cannot go back to random variables. So you have to be a bit careful. This is not like a distribution on RD. Distributions on RD somehow make sense. You can interpret them in the sense of testing. In the sense of testing, there's somehow an interpretation that a test function then is like a measuring device or so. But here, yeah, so this infinite dimensional distribution is really, by mathematical analogy, it works, but it doesn't really have any reasonable interpretation anymore. But it's very useful for the analysis. So in our analysis, we will encounter spaces with negative alpha and beta. And in the end, we will make sure that everything we output at the very end of the analysis, again, has positive regularity. By the way, I think these spaces are called Hida distributions. I'm not sure if it's exactly the same, but in any case, it's very closely related. Okay, so let's see what we did now. We started from this Burghers equation. I said we should work under the measure of the white noise. We now mapped this measure of the white noise to this sequence space, this Fock space. And then we identified this Fock space with some H00 and defined some more general Sobolev spaces, so to say, alpha, beta, for alpha and beta in R. So we did lots of technical work, but we're actually not really one step closer to making sense of the generator, right? So this should be now the next problem. I realized that I went quite shortly, but maybe this would actually be a natural place to already have a short break, and then after that I can pull through until the end, because somehow this is a natural place to stop, and otherwise I would do a break in 10 minutes where maybe it's not so natural. So is it okay, or should I continue?
Well, yeah. Anybody have a question?
Nicolas?
Yes.
You have sort of some examples of the guys that live in these negative alphas or negative betas.
Yeah, we will see. So the simplest example is so the generator of the Burghers equation. So let's say this we associate with an operator G, and then one simple test function we could. So now in this operator G we have to put something in, no? And so the simplest test function we could think of would be something like, let me write f here for f in C infinity. So just linear testing. So this is really the simplest test function on the space of distributions. And so let's call this f of u. And then g of f is in h minus 1/4 infinity, basically, and not better than that. I mean, it's not you don't see yet why that is, but this will be in the next talk. I will explain this. But so this is the prime example. That's why we need to work with these spaces. So you see that this is the nicest function you can work with. So this here actually is in the intersection of, yeah, so let's write it like this, as I did before. This is in any space you want. And you plug it into the generator, and well, it's well defined, but it only gives you something of regularity -1/4. On the other hand, in here, you still have good regularity, but in this, so the upper index is the regularity of the kernel. The kernel will be very irregular.
Thank you.
Anybody else have a question? Nicolas, how long do you want the break to be?
I think 10 minutes is good.
10 minutes. So we start at 36 past.
Yes.
Not too many people.
The question about the reproducing kernel Hilbert space construction. So what is this construction that you start from an orthonormal basis of? So one construction which somehow works more generally. Here we have the specific situation that we can construct these Wiener-Ito integrals, and this is maybe not so obvious how to do this on any Gaussian Hilbert space. And so the usual construction that I know, and I'm not sure if this is what you're referring to, is that you would take an orthonormal basis of the Hilbert, of the Gaussian Hilbert space, and then plug these into Hermite polynomials, and then basically take products of Hermite polynomials of these orthonormal basis elements, and then take the closure of that. And in the current setting, this should give the same, yeah, this will give the same thing. This is basically what I was alluding to with the Hermite polynomials. But I'm not sure if this is what you mean. Yeah, so in this case, okay, great. Yeah. In the white noise case, this gives the same thing. I think 30-minute break, no? So in the schedule, it's that now we go until 15 past, and then there's half-hour break until 45.
Yeah, I would propose we do the next session at the scheduled time at 4:45 UK. It's a bit late for you.
Yeah, that's good. Yeah. No, it's also good to take a break of half-hour between.
Yeah.
Should start in German time, sharp.
German time is 15 past now.
Oh, sorry. Is that CT, I forgot one of this word.
CT is 15 past, yeah.
CT, okay.
Okay, so let's now go about constructing the generator. And well, we'll do the easy thing again first. Now we first look at this Ornstein-Uhlenbeck process and construct its generator. I mean, we already basically could define its generator on cylinder functions, on simple test functions on our state space. But now we want to see how this guy plays together with the chaos decomposition. And this plays together so nicely, and this is actually the reason why this whole analysis works so nicely. Because this thing will just become a Laplacian. So let's see how we can see this. Remember what we just saw, Wn is the span. We didn't see this, okay. But you can show that the nth chaos, so the image of the n-dimensional functions, symmetric functions under this Wiener-Ito integration map is equal to the closure of the span of such Hermite polynomials where you plug in, I mean, before we had such a Hermite polynomial where we had to normalize the kernel phi here. Now we take from the beginning a phi which is normalized because we take the span so we can multiply with anything before. And yeah, so this is in L2 of one variable, right? So We integrate it against the white noise, and after that we plug it in the Hermite polynomial. So if we want to understand how the generator acts on something general like that, effectively it suffices to understand how it acts on this test function. Because after that, by a limiting argument, we can first go to this space and then to this space. So let's look at this and let's apply Ito's formula to this, where U solves that equation. Then we see that we get the first derivative. We have this term where we integrate the Laplacian by parts. It becomes this term. And then this term here becomes a martingale. We don't really care about what this martingale is because, well, it will go. So to identify the generator, we just have to identify the drift. And then we have the Ito correction, which is the second derivative. And now it does somehow become important what the martingale is, because now we have to identify the quadratic variation of the martingale. So now we separate drift and martingale part. This M tilde is this one together with this one. It's some martingale again, so that's okay. And now here, yeah, so this is the same. We didn't change anything. And here we just plug in the quadratic variation. So the quadratic variation gets a 2 coming from here. That's why we need the square root 2 here, because it now cancels the 1/2. So it's gone. And then, this here is the derivative of a space-time white noise. So the derivative goes onto the test function, which comes here. After that, we have to take the squared L2 norm of the test function because of the space-time white noise. And then we have dt. So this is our drift now. And now we want to massage this drift a little bit to see that it is something nicer. And for that, we can use recursive formulas for recursive relations for the Hermite polynomials. The first one is that if you take the derivative of the nth Hermite polynomial, then you get n times the hn-1 Hermite polynomial. You can check this by looking at these formulas we had, the recursive definition, for example. So this is hn-1. And well, here's the second derivative. So it's n-1 times hn-2. This thing, by integration by parts, we're on a torus, so there are no boundary terms. We can integrate by parts and pull one derivative onto the phi. So we can write it like this. There's a reason why we want to write it like that. And now we want to build the link again between, I mean, it's a bit awkward now how I write it, but we want to see it in chaos writing. So this here we saw is wn-1 evaluated in this function where we multiply phi n-1 times together with itself. And then this here would be evaluated in ut. And so this here would be a random variable which depends somehow on a white noise. And as that white noise, we would take the ut here. For the moment, I will take everything as stationary all the time. At the end, I will explain. So we don't need to take things stationary. We can be somehow absolutely continuous with respect to the stationary measure. But for now, just for simplicity of thinking somehow, let's assume everything is always stationary. So for each fixed time, this thing is a white noise. And then this here, well, it's just W1 of the Laplacian. And here, this, well, becomes Wn-2, and then we have this inner product here. And now the point is that by multiplication rules for the Wiener chaos, this product here can be written as an n-fold Wiener Ito integral of these functions multiplied together. So we have n variables now, n-1 go into here, the nth one goes into here. And the n is just the n from here. But it is not quite that. So when you multiply these together, it's not true that you get something in the nth chaos. You also get a so-called contraction, where you have to take one variable from this kernel and the variable from this kernel, and you integrate them together. And after that, you still have n-2 variables left here, and you put them into Wn-2. Well, and you have n-1 choices for the one variable you want to integrate out, so you get a factor of n-1. And so what I was just describing is exactly this term here. So this is Wn-2. We have n-2 variables left because we removed one here. And the one we removed, we have to integrate against this one. So this is this integral here. And the factor n-1 comes from the fact that we have n-1 choices here. So by these multiplication rules, this product is equal to this term plus this term. But since we subtract this here, this cancels exactly, and we only remain with this one. Okay, that's very nice, because now if we look at this thing, we see that the symmetrization of that, when we have n times somehow this thing, and we always hit the one-dimensional Laplacian on the last variable. But you could also take the n-dimensional Laplacian, where you take the second derivative in the first variable plus the second derivative in the second variable and so on, and apply that to that kernel. And this would just be exactly the symmetrization of this function. So actually what we have here is Wn of the n-dimensional Laplacian of this function phi multiplied n times together with itself. And this thing here was, I mean, this is what we started from, is linked to Wn. So we have shown that the generator on such a function is exactly again in the nth chaos, except that you put the Laplacian onto the kernel. So again, if now, I mean, this was for a very simple test function, but now by a continuity argument, you extend it to general functions with the chaos expansion, where all the kernels now have to be in H2. And then we see that the generator has exactly this form, that we get this series where now the Laplacian appears on each kernel here. And now this is notation, because I don't really want to work with these Wn's, and so I want to work on this Fock space. So I use L0. This is abuse of notation. This is in principle a different operator, but for a phi, which is a sequence of phi n's, in the same way. So just applying the Laplacian to each of the phi n's. So the generator on the physical space, so to say, and the one on the Fock space, I denote by the same symbol. Okay, this was the easy part. Now let's look about the let's look into the Burghers generator. So again, this is our Burghers equation, and we want to compute the generator on a generic chaos decomposition. And again, it suffices to start with Hn of u of phi, where phi has L2 norm 1. And well, this now is that there's no martingale part. So now we just see the first derivative and then this term here. And the derivative here we can integrate by parts. So we bring it here, this brings the minus. And then we use again that this expression here is n times Hn minus 1. Okay. Now we want to do the same kind of manipulations again. So write it again in terms of chaoses, use the multiplication rules for the chaos, and in the end, see somehow a nice-ish, I mean, it's quite singular, but relatively concrete expression for the generator. So this here is Wn minus 1 as before. This thing here, we can see as, so this is the product of, let me write this. I can write this as the integral over the torus of W1 Dirac delta in X, W1 Dirac delta in X, and then delta X phi X dx. And this thing here would be point evaluation formally. So that, yeah, I mean, the thing with the Burger, with the Einstein-Uhlenbeck generator before was rigorous. Now again, we're doing formal analysis, because I mean, I told you there's no known solution, weak solution of Burghers equation, which leaves the white noise invariant. So, I mean, even the starting point here is nonsense. But anyway, so the point evaluation is just testing here as the kernel with the Dirac delta, which is of course not in L2, so you cannot really do that, but let's ignore that. And then, well, we have the square of this guy, so we have to multiply this thing together with itself. Now, this, by the multiplication rules, gives us something in W2, where we take this tensorization, plus this contraction, where we have to integrate these two variables together. So the L2 inner product of two Dirac deltas. Well, this is infinity, so it's not well defined, but it does not depend on X. So it's an infinite constant. So if you would somehow regularize by putting epsilons everywhere, then you would get an epsilon dependent, possibly large constant. But then the point is, once you have a constant in this place, then you integrate a constant times the derivative. We're on the torus periodic boundary conditions, so this would drop out. So that's why this constant that we get from here is not seen, and we only remain with this W2. And now W2 is constructed as a continuous linear operation, so we can exchange it with this integral. So we can pull the integral inside, and we see that this is W2 of something like this. So we have W2 times Wn minus 1. And now we have to use, again, the multiplication rules on the chaos. So what happens when you multiply something with the second chaos with something in the n minus first chaos? Well, now there are going to be 3 terms because, well, we have 1 term without contraction and then 2 possible contraction terms. So here, the first one is just of n plus 1 variables where we multiply these 2 together. The second one is we take 1 variable from here, 1 variable from here, and integrate them against each other. And then we still have 1 variable left here and n minus 2 variables left here. So overall, n minus 1 variables left, which we plug into an n minus 1 fold integral. So this is, I don't want, yeah, let me be a bit fast here. So this is this notation with this tensor 1, this notation from Nuala's book that I'm using here. How many choices do we have for choosing one of the variables? Here is n minus 1, this explains this factor, and 2 choices here, so this explains this factor. And then we still have another possibility. We can contract both of the variables here with 2 variables from here. So to find 2 variables to contract here, well, we have n minus 1 choices for the first one, and after that, n minus 2 choices. So that explains this factor. And again, then after that, well, here we don't have any choice. We have to choose all the variables. And then we have this contraction where, well, we choose 2 from here, 2 from here. So after that, there are still n minus 3 variables left. And by applying this general rule now in our concrete setting, we get that this equation has the formal generator G given as G plus G minus, where G plus is this part here, which goes up one in the chaos, 1 order. G minus is this one, which goes down 1 order in the chaos. And this term actually does not appear. So for the specific kernel that we have in our problem, we can compute by a symmetry argument that this term will not appear, this term will be 0. It depends, I mean, everything here is formal, so to really make this rigorous, you would have to regularize, and then it depends a bit on how you regularize. But if you regularize in somehow shift invariant, nice enough way, then you can really make sure that this term drops out. And what are the kernels now? So in G+, we have something of n variables, and we go up 1 chaos. So we turn this kernel into a kernel of n plus 1 variables. And how do we do that? We take our kernel, we differentiate it in the first variable, and then we plug in everything from y3 to yn plus 1. So this is notation. This just means y3, y4, and so on until yn plus 1 with this colon here. And then in the first spot, we put y1, and then we have this Dirac delta here of y1 minus y2. And the minus and the n here. And well, then strictly speaking, you have to, so if you really want, yeah, so you should take the symmetrization, but yeah, let's ignore that. In G minus, let's maybe this is instructive also to see that we really have I always need to check this carefully, that we really plug the right number of variables into this. So here, this one takes n variables. So here we have n minus 1, right? And here we have an additional one. So these are n variables really. And then this y2 doesn't appear in here. This is the last one. So n plus 2 variables, n plus 1 variables. And in the G minus, we don't see a Dirac delta. So the G minus in a sense is more regular. We just double the first variable. So I have y1 here, And then after that, we plug in y2 up to yn minus 1. So overall, we plug in n variables because, well, we have n minus 1 variables, but 1 appears twice. So n variables, and we also have this derivative in the first variable here, the minus here, and some prefactors which come from these contraction rules from this one here. And we already had an n before on the slide before. Okay, so this is a computation. I'm not going to do this computation now. You can see this in the paper, but I mean, so the formal computation is basically just using these rules from what I told you before. And the rigorous one, you have to regularize it, and then you can do the same computation. But we see already, this already carries quite a lot of information, this expression here. Here we see that no matter what phi we take here, this thing will never be an element of L2. Because we take a smooth function, take as smooth as you want, but you multiply it with the Dirac delta. Well, after that, you will not have anything in L2 anymore. So it cannot happen that this G plus puts out something, some kernel in L2. We can never get positive regularity for this one. We can only get negative regularity. And in G minus, well, this thing here could actually be quite smooth. So if your phi n is smooth, then this here could still be a smooth function. But this is a singular operation if you don't plug in something smooth. So a priori, the phi n is an L2 function. And the diagonal here of, well, this two variable diagonal is of course a null set with respect to Lebesgue measure. So we're trying to evaluate an L2 function on a null set. And this we can only do if we have some minimal regularity. So two takeaway features, which will also show up in our estimates. G plus can never output very good regularity. G minus can output good regularity, but the input needs a minimum amount of regularity. Otherwise, we cannot control anything. Okay, so now notation again, we define these operators. So this G as G plus and G minus, again, also on Fock space with the same symbol, or on maybe some Sobolev spaces. Actually, on this space is not defined because we need regularity, like I said. So it has to be defined on some Sobolev space with positive regularity. And this is again, is the same expression as before, except written a bit differently. So now we say that what is the contribution to the nth chaos of G plus of phi? And of course, this is coming from the n minus first chaos of phi. And the contribution to the nth chaos of G minus is coming from the n plus first chaos of phi. Another important observation is that G plus is minus the adjoint of G minus. So yeah, we have this relation here on the Fock space or on sufficiently nice subspaces of the Fock space. And in particular, since G is the sum of these two, we see that the G is skew symmetric, anti-symmetric. So if we bring it to the other side, we change the sign. And this will be very important for the analysis. Okay, now estimates. Let's try to see where this operator G really is mapping and what input we can have. So remember again, this Sobolev space we defined in this way, where we had this H2 alpha here and this 1 plus n to the 2 beta here. And now the point is that this H2 alpha is up to some prefactors of order of 2 pi. Basically the same as taking 1 minus the Laplacian to the alpha of phi n, because if you take the Fourier transform, then you get a Fourier multiplier from this thing, which is basically 1 plus k squared to the 2 alpha. I mean, to the alpha, and then you take the square of the Fourier mode, so then it becomes 2 alpha. And this thing here is just 1 minus L0 to the alpha applied to phi. And so this is the evaluation of that on the nth chaos. So this alpha beta space can be written differently up to equivalence of norms, factors of 2 pi, as 1 plus n to the beta, 1 minus L0 to the alpha acting on phi, and then you take the L2 norm of that. And right, so this n here is this operator, which in quantum mechanics is called the number operator. In stochastic analysis, it's called the Ornstein-Uhlenbeck operator. So just take the nth chaos kernel and multiply it with n. Very simple operation. Now, estimates. What with this notion of regularity now, what can we say? So the generator for the Burghers part of the equation satisfies the following estimates. So I told you that to control the G minus part, we have to put in some regularity. We cannot just put in an L2 function because we would try to evaluate an L2 function on a null set. So the assumption is we plug in something, some kernels which have regularity bigger than 1/4. Beta can be anything at once. So then we take a function which is in H alpha beta, so alpha bigger than 1/4, and we get out something which has regularity alpha minus 3/4, and then here beta minus 3/2. So we lose 3/4 in the alpha variable in the L0 regularity, in the spatial regularity of the kernels that appear, and we lose 3/2 in the decay of the Fourier modes, of the chaos, sorry, of the chaos kernels. So in the decay of this n here. On the other hand, for the G plus, and one remark is that this thing here can be arbitrarily regular. So if alpha is 10, then this here is nearly 9, so 9.25. So this can be super smooth. So the G minus can output L2 variables. It's very easy. Just have to put in something smooth enough. On the other hand, the G plus, for this we have the following estimate. We need alpha to be less than 1/2, and then we can lose 3/4 regularity and map to alpha minus 3/4. So of course you can plug in something which has much better regularity, but you cannot make use of the regularity in alpha. Everything you can use is 1/2 at most, more you cannot use. And so at best here we output minus 1/4. In the beta variable, there are no constraints. And again, we lose something, but we lose a bit less. We lose only 1. And this is actually also, I mean, looks a bit arbitrary. Here we have 3/2, here we have 1. But this 1 here is absolutely crucial. If we would also have 3/2 here, then this would be the end of the story. We wouldn't be able to do anything anymore. We really, in the end, carefully have to make use of the fact that there's a 1 here, and that through some other argument, we can gain back 1. And like this, we can somehow make sure that we effectively don't lose something in our analysis. But this will, I will explain this on Thursday. Yeah, so these are our estimates. And this is again what I said. This one can only output distributions, only something of negative regularity. And it's not surprising because I'm multiplying something with a Dirac delta. And if I plug in, no matter what I plug in, well, if I multiply with the Dirac delta, after that, it will not be an L2 function anymore. And again, here, because of this evaluating on the diagonal, we need some minimal regularity to control this expression here. So this means effectively that we cannot find a domain for this operator. There exists no phi such that G plus of phi is in L2. And this is, in principle, I mean, this idea that this G operator can be defined as with an output in distributions on an infinite dimensional Gaussian space this was already observed by Assing in 2002, not with this precise error analysis here or regularity analysis, but this observation that you can make sense of this as a distribution is actually due to Assing from 2002. Okay, so our goal is to construct a domain for the operator. Now we said that at least G plus cannot have a domain. It's just not possible. You cannot find any function which is mapped to L2 by G plus. So the question is if this is the end of the story, and of course it's not. And to understand why it is not, well, we should go back to regularity structures. So by the philosophy of regularity structures, we should really see the nonlinearity as a perturbation to the linear equation. So translated to our operators, we should really see L as a perturbation of L0. So this G here should really, in some sense, treat it perturbatively, and we cannot hope to control it directly. We should control it using this L0. So directly controlling G would be somehow a different order of difficulty. In terms of processes, controlling this G would be constructing the KPZ fixed point, which is extremely difficult now. And I mean, there's a description now, but it's somehow very, very difficult work. While constructing this sum here is solving the KPZ equation, which by now maybe is not easy, but is something which we understand really well, for which we have many tools which we can do well. So really it is much, much easier than dealing with this thing without the L0. And we should make use of that. We shouldn't try to tackle the G directly. We should combine these two. And one way how we could do this, we can see from finite dimensions. So we can understand by looking at a finite dimensional analogy. So this is our Burghers equation, and we have this part here, which in some sense we now understand we can interpret as an infinite dimensional distribution. Our state space is infinite dimensional, and on this state space somehow we can see this as a distribution. Well, rather than directly going here, let's try to look at an analogous finite dimensional problem. So this would be an SDE where we plug in the solution into a distribution on a finite dimensional space on RD. And then we have an additive noise here. So this thing, if this is a distribution, the formal generator G associated to this part here would be the inner product of B with the derivative of F. And again, this thing cannot be a continuous function. And there exists no F such that this thing here becomes a continuous function. You cannot just multiply a distribution with something and then get a continuous function. I mean, to even make sense of this product, you need some regularity of F so that this thing here is still a continuous function, and then multiplying the two together, there's no cancellation of irregularities. You will get back something which has the same regularity as B. So it is impossible to find a generator for just this problem. And now if you think about it, finding this generator would mean that you solve an ODE where your solution is running through a distributional field, distributional vector field, but this really doesn't make any sense, right? So it's not surprising that you cannot do this. However, and this goes, as far as I know, back to a paper by Flandoli, Rousseau, and Wolf, although there have been many, many works in this direction. For example, there are also nice works by Delarue and Diel and Kanizawa and Chuk recently using rough pass paracontrol distribution methods to push this further. But the idea is always the same, that, well, the full generator for this problem is not just this thing, but also 1/2 the Laplacian. So we should make use of that. And what they do in that work is they solve the resolvent equation. So this here is a PDE, which we can rewrite separating this part and this part as follows. U is equal to lambda minus 1/2 Laplacian inverse. And then here the product of B and the gradient of U plus F. F is some continuous bounded function, let's say. So we want to, I will explain in a second then why this is useful to solve it, but let's say we want to solve this for some right-hand side, which is given and continuous and bounded. And let's say now the B has C minus alpha regularity. If you don't know what that is, it's not so, it's just an analogy here, just a story, but so you can picture it's in the end, alpha will be less than 1/2. So we're here between -1 and 0. So you can think of this as a first order derivative of something of regularity 1 minus alpha. And so 1 minus alpha now is positive. So it's a Hölder function. And we take the derivative in the sense of distributions. So if it has this regularity, then this product should at best have the same regularity as B. So it should also be minus alpha. And then here we gain two derivatives. So the U will be in C2 minus alpha. And so therefore taking a derivative loses 1 degree of regularity. So we're in 1 minus alpha. And here this is 1 minus alpha. And then there's this rule that you can multiply a function with a distribution if the sum of the regularities is positive. So we need this plus this to be positive. So we need alpha to be less than 1/2. And in this case, this equation here is well posed. And this comes from the fact that this Laplacian here gains two derivatives. And then we can solve this equation. And we see that L, so once we have a solution to this equation, L of U, just bring it to the other side, is lambda U minus F. And we saw that the solution will have 2 derivatives more than v, so it will have 3/2, somehow c3/2. And this here is also continuous and bounded, so this here is continuous and bounded. And so we have found a domain for this operator. Yeah, so this operator in itself has no domain, but by solving the resolvent equation, we have found a domain for this operator L, for the sum of the two. And once we have a domain, we can define what it means to be a solution to the martingale problem. And then we can show that there exist unique solutions to the martingale problem. So in this way, you can construct solutions to STEs with distributional drift through a martingale problem. One remark here, actually for the solution to this equation, so this thing in itself will not be a continuous bounded function. And also this thing in itself will not be a continuous bounded function. So the solution has regularity 2 minus alpha, which means if you hit it with a Laplacian, you go back again to a negative regularity space. So this here is a distribution, this here is a distribution. But the point is that we prepared the function very carefully by solving this equation. We chose a very specific function, which is such that the singularities, which you get from here and here, cancel exactly. So all the singular part cancels and we remain in the sum with something that is continuous and bounded. Okay, now, yeah, to summarize, what did we do in this finite dimensional space, finite dimensional problem? So we want to solve this SDE where B is a distribution. We can do this by solving the martingale problem for this operator. This one we could call L0 in analogy with what we have in our situation, and this one we could call G in analogy. And then we construct the domain by solving the resolvent equation. And yeah, we can solve this resolvent equation if B has regularity minus alpha, where alpha is less than 1/2. If you go beyond that, so with regularity structure style techniques, you can go down all the way to -1 if you can construct suitable, somehow enhanced versions of this B. And all this is based on the regularization effect of L0. If we wouldn't have the L0, there would be no hope to carry out this program. No. So can we implement this strategy for our operator now, which, I mean, just from notation looks very similarly, no? Maybe our space is infinite dimensional, but maybe we can still just implement the same strategy. And I think until the break, I can now still explain why this fails. And then after this half-hour break, we can see what else we have to do to overcome this problem. So the resolvent equation is, yeah, just choose some right-hand side and we work on Fock space here. Of course, if we can construct a solution which has positive regularity, then we can associate a random variable with it again. And then we can go back to the physical world of random variables, so to say. And we split this L again up into L0 and G. And we bring the G to the right-hand side. So this is exactly the same thing we just did for the previous finite dimensional problem. And here we invert lambda minus L0, which we can do, I mean, so on the Fourier side, it's easy to see that how you can invert this thing here. It's just Fourier multiplication, right? And so if alpha is bigger than 1/4, so this is an input, we have to assume this, that this G minus then can be estimated losing 3/4 regularity in the alpha variable and 3/2 in the beta variable. On the other hand, so here we need alpha bigger than 1/4. On the other hand, if alpha is less than 1/2, then for G plus we have a similar estimate, except we only lose 1 in the beta variable. And what's also easy to see is just by going to Fourier side, that we have regularization effects of this operator. So if we invert this operator, then we can gain delta regularity, where delta is between 0 and 1. We can gain up to 1 degree of regularity in the alpha variable compared to the right-hand side. And if we gain less, then we can use this to gain a factor in lambda. So you should think of lambda as being big, and we choose lambda big in the end to get a contraction. And so, for example, here we lose 3/4, so we could imagine that we choose delta to be 3/4, and then here this would still be 1/4, so we would still have lambda to the minus 1/4 left. And now let's try to combine all that and do a Picard iteration for this equation. So we plug in, so first of all, what space should we take? Well, beta, we don't really know. Let's leave it variable by now. Alpha, well, somehow the alpha here has to be bigger than 1/4. Here it has to be less than 1/2. So it's natural to just take 1/2. That's the most canonical point within 1/4, 1/2. So we plug in something. Okay, I should have written 1/2 here. Okay, yeah, so okay, this is for apparently for alpha. So this analysis now is for variable alpha, but so alpha between 1/4 and 1/2, and you should think of alpha as 1/2. Doesn't matter so much. The point is something else. We apply, so we take an element from this space, we plug it into the G, and then we compute the right-hand side, and then we want to show that we have an element from the same space. This is the first step that we would have to do the Picard iteration. But when we apply the G here, we lose in alpha and we lose in beta. We have 3/2 because 3/2 here and 1 here, and the worst of the two is 3/2, so we lose 3/2. Then we invert this guy, which means we gain in the upper variable. So we gain actually more than, so 3/4 is okay, but we actually gain 1 full degree of regularity. So we actually would go back here to alpha plus 1/4 on the right-hand side. Or we only use 3/4 and then we have a small factor left. But the point is that this operator doesn't touch the beta regularity at all. The beta regularity is looking at how quickly our kernels are decaying. And this thing is regularizing each of the individual kernels, but it's diagonal on the chaos. So it is just acting on the nth chaos and is not multiplying it with any n dependence. It's just really inverting the Laplacian on the n-dimensional variables. So we cannot close the Picard iteration because we started from this space. And yeah, let me correct this here. So we started from this space, but from this space, but we mapped back to a worse space. And so therefore, it is not quite so simple as in the finite dimensional case. We need to do yet one more thing to overcome this and to construct a domain. I mean, it will be a variant of solving this equation. But yeah, for now, let me stop here and let me explain then. Let me see if, yeah. Let me explain then after the break in half an hour how we can go forward and overcome this loss of regularity in the n variable.
So, okay, so thanks, Shumei. Anyway, should we just unmute everybody and applaud? But I still don't know. Andres, can you explain to me how to unmute everybody?
I don't know how to unmute. Hello? Yeah, sorry, I wasn't. I was muted. Yeah.
We can do that here. Can we unmute everybody?
Yeah. Does anybody have a question or anything before we take the break?
Yes, I have a question. So Nicolas, Martin, I also hinted on that yesterday. Why, or can you comment on, you mentioned that G should be the generator of the KPZ fixed point. Can you comment on that, say something about that? Why
yeah, so,
it should be the case?
Maybe I make an empty slide. So if you take the Burghers equation, and we apply the KPZ scaling where, okay, I don't know how this looks like on the level of the Burghers equation spontaneously now, but let's say we apply KPZ scaling. Then we get a new equation with this. So the generator of this equation is epsilon L0 plus G. And so now this is somehow KPZ scaling on a finite scale, but now we should send epsilon to 0 to pass to the limit. And this should then be the KPZ fixed point. And so this should formally be the thing with only this operator G. And there's a, I was deliberately quite specific about that when I said, let's look back here. I said there cannot exist any domain for G plus. Right? I did not say, I don't know if there can exist a domain for G. So G is the sum of G plus and G minus. So G plus and G minus, so if you want to understand what's happening on the nth chaos, somehow you have something which comes down from the n plus first, and you have something which comes up from the n minus first. And this thing which comes down cannot be in L2, but it could have some cancellations, just like we saw in the thing with the Laplacian, that these two things cancel. That being said, if you look now at the constraints we have here, these two constraints, it's exactly incompatible. So they're exactly so that you cannot really make this work. So the image of this operator yeah, okay, I have to sort this in my head. In any case, it's so that, yeah, so this, I mean, this, you see that they're separated, okay, here by 1/4. Okay, I'm no, sorry. This part actually, I'm confusing. There's another result. You can have a better estimate if you choose alpha less than 1/4 here. Then you can, no, alpha bigger than 1/2 here. Then you can replace this 3/2 with a 1, which at some point was important for me. And then this looks really bad because then here you need one bigger than 1/2 and you need less than 1/2, and somehow they're not compatible. But actually in this way you do have some overlap. So in principle, it could be possible that you have this cancellations from G plus and G minus. But yeah, it's much more difficult than using this L0 operator to regularize everything.
Right. If there's no, I see there's a chat. What to say? Yeah, thanks. Okay, that was a thanks. Right. Do we start like a code 2 as scheduled?
Yeah, I think so.
Okay, good. So have a nice break.
Okay, good. Okay. Perhaps I just stop the